Good evening, everyone. It is once again Ted the Speed Learner, and in this particular video I'm going to cover parametric functions and Bezier curves. Now, what is a parametric function? Well, this particular word right here is derived from two Latin terms. The first term, para, is derived from the Latin term which means beside. The other one is derived from the Latin term which means measure. So we're going to have a beside measure. That's what we're going to have. Okay. But this is called a parametric function. Well, what is a function? Well, I covered this topic in a previous video. If you don't believe me, you can go through my mathematics playlist on my YouTube channel and you can look up the function videos. But basically it goes like this. You have the f of x right here. Okay? And this goes kind of along the lines of the Cartesian coordinate system. Now, do you remember that? I covered that in a previous video too, but I'll give you a brush over on that one. You have this. This is called the horizontal axis, and it's usually that's usually marked with the letter x, okay? With the variable x if you want to go with that. And this is the vertical axis, and it's usually denoted by the letter y, or the variable y. So, let's say it again. The horizontal axis is denoted by the variable x, and the vertical axis is denoted by the variable y. Okay? Now, we could also go along and change that y, which we do in functions, to the f of x. That means we can come up with an equation like this. Hang on. Okay. Now that means that whatever value we give for x, there will be only one value for y. Okay? So, let's say we say that x is 1. Well, the only answer to 2 plus 1 is 3. So this equation is quite true right off the bat. So, instead of saying y over here, we're just saying the f of x instead. We've replaced the y with the f of x. That's all we've done. And that means that for every input, there will be one and only one output. Okay. Now, let me give you an illustration about parametric functions. Okay. Now, parametric functions kind of expand on regular functions. Okay. Let's say you own a business, and the business sells winter coats and ice cream. And let's say this particular business sells these winter coats and ice cream all year round. Now then, during certain periods of the year, winter coats sell better than ice cream. And then at other parts of the year, ice cream sells better than winter coats. Now, does that mean that when we start selling more ice cream, we're just automatically going to sell less winter coats? The reason why we're selling less winter coats is because we're selling more ice cream? Is that what we're trying to say? Absolutely not. We're trying to say that during certain times of the year, more ice cream will be sold, and at other times of the year, winter coats will be sold. Do you know why that is? Mostly due to temperature. Let me tell you something. when the temperature outside is below freezing, we're obviously going to sell more winter coats than we're going to sell an ice cream. Now, when that temperature suddenly skyrockets to near 80 degrees, obviously we're not going to need near as many winter coats as we do ice cream. So, we can show a relationship between the winter coats and the ice cream due to temperature by use of the parametric function. How do we do that? Well, we can do something like this. And the T will represent the time of the year, whether it be winter, spring, summer, or fall. We'll assign the numbers 1 through 4. Okay, we'll assign the numbers 1 through 4, and we'll say 1 is winter. We'll put a W there. 2 is spring. We'll put an S there. 3 is, well, let's put an SP, and then we have an SU for summer. And then we'll have a 4, which is F. Okay? W for winter, SP for spring, SU for summer, and F for winter. For fall, I'm sorry. F for fall. Okay? So anyway, let's just simplify this. Okay, so we know that 1 is winter, 2 is spring, 3 is summer, and 4 is fall. Okay, so let's say that the F of T, in this particular case, is and this is a poor illustration. I will actually make another video that will show this a lot better than what I'm showing here, but this is kind of the way it works. Then we can have the G of T here. Okay. And let's say well, that's really kind of okay. So we can actually say T represents the time of the year, and let's say that the 5 here represents the price of the ice cream. And the G of T would have T plus 80, and the T here would represent the time of the year, and the 80 would represent the amount of money you're going to spend on that coat. Okay? And eventually what happens when you, and like I said, this is a very poor illustration. I will give a much better illustration in a later video, so don't hold this one against me. This is just kind of a intro thing, and this one's pretty flawed, as you can plainly see. We got much better than this. But eventually what you have here is, okay, now what you're going to have here is these X and Y coordinates, which we're actually going to change from X and Y to the F of T and we're going to change this to the G of T. Okay. And eventually we'll be able to form things called parabolas. Now, what is a parabola? Well, you can have something like this. Okay? And this parabola would show the relationship between the sales of your coats, well, this would be the sales of your ice cream and the sales of your coats. And then the T part would actually be this right here. See what I mean? Now you say, well, that's a horrible illustration, but you're getting the basic understanding of parametric functions. What it is, it's showing the relationship of 3 different factors: the sale of your ice cream, the sale of your coats, and the time of year that each one is selling. Remember, you're selling the winter coats and the ice cream all year round. And you want to see which one is performing better at a particular time of the year. And that's where you start coming up with all this. Alright? But like I said, this is an absolutely awful, terrible way to illustrate all this. Alright. So, there is a type of parametric function, and hopefully this will be a much better illustration here. But there is a type of parametric function called a Bezier curve. Now, obviously, this is a French word. Bezier is a French word. Let me give you a slightly better illustration here. Okay. Let's say we have this mountain. Now we got a mountain. There's one guy at the bottom of the mountain, and there's one guy at the top. Now this kind of goes along the lines of linear interpolation. Now, do you remember what I talked about, what I discussed in linear interpolation? I had a video up there that says linear interpolation. If you don't believe me, you can look up linear interpolation through my YouTube channel. You can find that particular video. It was uploaded not too long ago. But anyway, this here is going to become one linear interpolation, and this was going to become another one. Now, we know that this guy is at the bottom of the mountain, and we know this guy is at the top. This guy wants to go up the mountain. Okay? And this guy wants to go down the mountain. Let's say this guy is really hot, okay? He's down here at the bottom, the sun is shining, it's beautiful, it's 70 degrees down there, and he is just, well, maybe not even 70, let's say it's more like 80 and balmy right down here at the bottom of the mountain. He is just hotter than a firecracker. This guy up here on top, it's a big, huge mountain, and he got high enough where he's about ready to freeze. Okay? Bottom of the mountain is hotter than a firecracker, but this guy up at the top, he's got snow and ice. He is freezing his behind off because he's climbed so far up the mountain that he's freezing. He wants to come back down because he's tired of freezing. And he knows if he comes back down far enough, he's going to be warm again. Okay. Now we can divide this up into little segments. This is 10% up the mountain, 20, 30, 40, 50. You get the idea. Okay, we can measure how much progress this guy is making as he's slowly climbing up the mountain and getting himself a little cooler. Now we also have this other guy, and we can watch as he goes 10% down the mountain, 20, 30, 40, and 50, and so on and so forth. Okay. Now, let's say we're really goofy people. Not only do we want to track the progress of this guy going up the mountain and this guy going down the mountain, okay, but we also want to know how far apart these two guys are from each other while this guy is going up and this guy is going down. Okay? So when this guy is 10% up the mountain, this guy here is going to be 10% down the mountain. Now we can draw a line between that one and this one. I know, that's a butt ugly line. And when this guy gets to 20%, now I'll go ahead and let's draw this a little bit bigger so you can actually see this. Okay, we're going to make a slightly bigger mountain here. There's your slightly bigger mountain. We got this guy up here, we got this guy down here. Now he goes 10% up and this guy goes 10% down. We can actually draw a line that connects this guy to that guy. Now, he goes another 10% up the mountain. This guy goes another 10% down the mountain. Now we can connect another line between this and this. As you can see, there's an intersect point right there. This guy goes up 30% the mountain. This guy's gone down 30% of the mountain. So now we can connect up. And there'll be another intersect point, say right here or something. But anyway, as you continue drawing these lines, connecting these two, let's say we go 40% and 40%. Now you're going to draw a line. Whoops. That's a terrible line. Okay. Okay, so somewhere along here there's another point. And eventually, as you draw these lines together, what you're going to do, eventually, okay, let me erase this down. As you connect those little lines, as you noticed, the distance between the two mountain climbers grows closer together up until they get to the 50% point. Okay, when the first guy's up 50% of the mountain and the other guy's down 50% of the mountain, the distance between the two of them closes in. And then it stretches out again. So eventually what you have here, we'll show you this with the mountain, is you'll have nice little parabola. And this nice little parabola that's formed because the distances between the two climbers, as one's going up and when the other one's going down, that's called a Bezier curve. You say, well, what is the usefulness of the Bezier curve? Well, that comes in SVG, Scalable Vector Graphics. Okay, so this is why I presented all this to you tonight. Alright? Because when you're using scalable vector graphics, what you're doing in essence is you're forming a triangle. Obviously, this is the triangle here. And the curve is inside the triangle, like this. This is called a control point. CP for control point. Now this control point controls two things about this curve. Alright? The first thing it controls is how far away this top of the curve is from this line right here. So that controls how far out it is. It also controls the width of the curve. Okay? The more this stretches out, the more narrow the curve is going to be. But the farther away it is, the wider the curve is going to be. So this control point not only controls how far out the curve is, but how wide the curve is too. And that's why I had to present this. This is the way that curves are drawn in SVG. Now I will definitely give a better example of this in my next SVG presentation. But when you're combining linear interpolations, what you're doing is you're forming a parametric function. So if you have two linear interpolations and you put them together, you form a parametric function. And one type of parametric function is called a Bezier curve. Now then, can you have more than one control point for a Bezier curve? Well, yes, because if it's like this, it becomes a quadratic Bezier curve. What if you want a cubic Bezier curve? Well, you might want a cubic Bezier curve. Okay? So, what would a cubic Bezier curve look like? Well, what you do is instead of having a triangle, you'd have more like a trapezoid. You have control point 1. You'd have control point 2. And these two control points would control not only how wide this parabola is, but how far out it is too. So like I said, you can have a quadratic Bezier curve, which is what I showed you previously, or you can have a cubic Bezier curve, which is what I'm showing you now. So, you can either have one control point or two. And I will show you a better illustration of this in my next SVG presentation. But now you know basically what a parametric function is and what a Bezier curve is. And like I said, I will do better videos on this subject. This is not the last time I do this, because I'm sure you'll want better equations. And you can even do research on this stuff and see much better equations than what I did. What I did was a poor illustration just to kind of give you an introduction to it. Matter of fact, that's what the title of this video is Introduction to Parametric Functions and Bezier Curves. So obviously we're going to do a lot better stuff than what we're doing here. But you're kind of getting the idea about this. At least I hope so. Anyway, I will definitely give you a better illustration in an upcoming video, but you now actually know what's going on here. And when I do my next SVG presentation, you'll know the difference between a quadratic Bezier curve and a cubic Bezier curve. The nice thing about these cubic Bezier curves is you have more control over the parabola. You can control exactly how wide it is, and you can control exactly how tall the parabola becomes, so on and so forth. You have much better control over this parabola with a cubic than you would with a quadratic. It's the only difference. Alright. Well, I thank you very much for watching this particular presentation. I will be presenting the Bezier curve in my next SVG presentation. And I hope you guys all have a good evening. And until next time, I'd like for you to stay tuned.